we are continuing from where we stopped last time. So we have our solutions of triangular equations. So triangular equations, earlier on you have seen matrices written in this format. I don't know if people are familiar with this kind of matrix. I would prefer to use a 3 by 3 because people are more familiar with it. Let's say this is 2 by 2. That's a 2 by 2. This is 2 by 3. Then this is a 3 by 3. Then these other positions are zeros. So this is what we call, this is like an upper triangular matrix. This is upper triangular matrix. Then we also have a lower triangular matrix where this is A11 now, this is 0, this is 0. A21, A22, this is 0. The diagonal is there, but the other entries are not really there. This is A31, A32, this is A33, something like that. So these are the lower triangular matrices. Lower triangular. So this is what we are going to be talking about. So that is the lower triangular matrix. Those are the ones we are going to be talking about, and our interest is in that. We are going to still be solving our AX equals to B system. However, now the A is either an upper triangular matrix or a lower triangular matrix. So now this is going to be, and delete that, delete that, delete that. So we can begin with the definition. We can begin with this definition. A triangular matrix is basically a system whose associated matrix is a triangular. So we can try to define like a triangular system is a system whose associated matrix is a triangular matrix. System whose associated matrix is a triangular. It's a system whose associated matrix is a triangular. Whose associated matrix is a triangular matrix. This is a system whose triangular system whose associated matrix is a triangular matrix, which can be upper or lower. So this is the system that whose associated matrix is a triangular matrix. Is a triangular matrix. Whose associated matrix is a triangular matrix, and this can be upper or lower triangular matrix. Okay. Then we can try to look at how to solve these triangular matrices. So how to solve these triangular systems. So how do I solve them? So given, so let's say now I have my A. So if I'm to suppose, so now I'm supposing that my A is a lower triangular matrix. My A is a lower triangular matrix. So if my A is a lower triangular matrix, meaning that, for my problem ax equals to b. Now I have like lower a equals to b. But we know that this A is an R by N matrix, therefore even my L must be an R n by n matrix, something like that. So therefore my Lx, so what do I have? So I have this is A11, this goes up to 0 somewhere, this goes up to AN1, this goes up to ANN will be there, even the diagonal matrices will be there, even these ones will be there. Can call this L, because this is L, can call that L. So can have that, but all these remaining ones, there is a 0. Let's say you can choose to put that, and this comes to this, and is L1, this is, okay, can put like 2, such that people can really do this in their mind very well. So this can be like L1, 2 goes to 0. This can be like L21, L22, this is a 0. This is up to 0. These remaining ones are zeros. LN1, LN2, but these ones are zeros. Everything apart from this is LNN. The ones in the diagonals are okay, but the rest are zeros. The ones up above the diagonal, they are zeros, and this is, if this is LX, then this is X1, this goes up to XN, and this is equal to B, this is B1, and this goes up to, Bn. So we have something like that. Therefore, how do we solve this? So if I want, do you remember I want to solve this kind of triangular system, and I've begun with a lower, if A is a lower triangular matrix. So how do I solve? If I begin with L1, this is L11 times X1, this is equal to B1. So therefore, I have that my X1 will be equal to B1 divided by L11, something like that. You can say I also have my L22, this is X1 plus L22 X2, and this is supposed to give me B2. So therefore here I see that my X2, because I already have X1, so I can substitute it here to get X2. So this is going to be B2 minus L21 X1, I got it initially, then I will have to divide this entire thing by 1 out of L22. So what do I get? So that is X2. We can also try out X3, which is L31 X1 plus L32 X2 plus L33 X3, and this is B3. So if you still try to solve, you find that this is going to be B3 minus L31 X minus L32, this is X1, L32 X2, and this entire thing is still out of 1 out of L33. So what do I get? Therefore, you find that. So we can do this up to, let's say, some xj that we are not aware of. So we can write an algorithm of how to find these values of x to some xj that we are not aware of. So this xj is going to be given by bj minus the summation. You remember I'm subtracting these two, this and that. So this is minus the summation minus the summation of what is changing. What is changing is basically the row. The column is not changing, so meaning I have I is the one changing, and this goes up to I minus, because this is a 3, so this will be j minus 1, and which is L. J remains the same, it is the I that I want to change. Then this is also xi. This is I. This is j. I really want people to see it clearly. This is j, this is I. xi. So this, however, at the end of it all, I have to divide by L3, Ljj. So that is my Ljj. So this is the algorithm. Later I will try to do this on MATLAB for the lower triangular systems. So that is the algorithm for the lower triangular system that we can use to find the values. If you have this kind of system and you want the solution, you can use this algorithm. However, you need to know the previous value. If you're calculating for x2, you need to know x1, because you will need it. Now we can also do the case for upper triangular systems. Upper triangular system. We can also try out the case for upper triangular system, meaning now in this case my A is a U, is an upper triangular system. So what do we have? So this is, so meaning my system is of the form A U equals to that. So therefore my UX, this is equal to be A11. Can call these U's U11, U12. This goes to, let's say, U1N. And this is a 0, U22. This goes up to U2N. This is a 0. That is now a 0. This is U, N, N. Something like that. Everything that is below the diagonal is going to be a 0. The ones up we're okay with them, but the ones below the diagonal are going to be zeros. So this is times x. So this can be x1, x2, this goes up to xn, and it's still the same as this is b1, b2, up to bn. So what do you get? So therefore this is going to be u1. So if I'm solving now, so I want to get, this is u1. Actually, for these ones you begin from down, un, you begin from this one here. So my un equals to, my un xn equals to bn. So you find that my un, so you find that my xn is equal to bn out of unn. If someone wants un minus 2, you see that my un, that is un minus 1, this is going to be column un minus 1, this is, that is the row, and this is the column. This is times xn minus 1 plus, this is now will be u, the row is still n minus 1, but the column is n. This is xn minus 1. Yeah, yes, this will be xn minus 1, xn minus 1, this will be x. Okay, it's confusing me a little bit. I will be up here. So this is supposed to be un. The column is n, un minus 1, n. n minus 1, column n. This will be xn. And this last one, this must be xn here. So this is equal to bn minus 1. So you observe that therefore my xn minus 1 is going to be equal to bn minus 1 minus 1. So this is un minus 1, n, this is xn, and this entire expression is divided by 1 out of un minus 1, n minus 1. Something like that. Therefore you find that my general expression, in case I want to solve, this one remains the same. So this is bj minus the summation, because I perceive there will be something there. So this one remains the same. So this should be uj, doesn't change. So that is uj. What is n? N is the I, so this is I equals to 1, but it goes up to what? It goes up to g, because if this is xn minus 1 and this is n, meaning it goes up to j plus 1. So this is I, n I. I is the one changing, comma, to represent the index times xi, and this entire thing is 1 out of, now this is 1 out of u jg. So this is also the algorithm that we shall use in case we want to solve a upper triangular system. So this is the algorithm. That is the algorithm that we shall use. Okay, so we can proceed. So we see that I think we should all know that. Note, in case I have my triangular matrix and I need its determinant. The determinant is the multiplication of all the entries in its diagonal. For example, if I have my A, and it is A1, A12, A13, this is 0, this is A22, A23, this is A33, and this is a 0. It's a diagonal matrix, so you find that the determinant of this A is equal to A11 times A22 times A33. So the determinant of a triangular matrix is the multiplication of the entries in its diagonal. So we should know that. So even if it is the other way around, for the lower triangular, it's still the same thing. Just multiply the ones in the diagonal. Okay, so you can try out this example and see using the algorithm that we have developed. So if I have my 1, 2, 3, 0, 1, 2, 0, 0, 1, and you multiply it with x1, x2, x3, and let's say it gives you 4, 5, 6, something like that. So if you try to solve this, what value do you get? What value do you get? So you try to solve. What values do you get? Okay. Now there are various methods, so you try to find the x1, x2, x3 using the algorithm that we have just defined. Now you find that yes, we can solve if we have the triangular systems, we can solve them that way. However, we also have a Gaussian elimination method that we can use to solve such linear systems. So I want us to go through it. So we have what we call the Gaussian elimination method. As we go on, I'll be referring it as that. So the Gaussian elimination method, the idea behind it, is that if we are given our system AX equals to B, what we do is that we change. We already aware how to solve the system if we have a triangular matrix, lower or upper. So we change the A into a triangular matrix. That's the idea. So we change the A into a triangular matrix. So so if, for example, if I'm given my matrix, for example, if I'm given my thingy, which is x1 plus 2x2 plus 3x3 equals to 1, I'm given my x1 plus 2x2, let's say minus x3 equals to 4, negative x1 plus 6x2 plus 7x3, this is 7x3 equals to 5, and I want to solve this. I can generate my A, which is 1, 2, 3, 1, 2, minus 1, this is minus 1, this is 6, this is 7. And as far as what the Gaussian elimination method says, you just have to transform this. Can make this a little bit simpler so that I can play around with the echelon forms. If I make that such that this is 1, 1, yeah, something like that. So what do I do? I just play with it in simple, because if I'm to transform this, take it to don't forget B also. B will also be changing, so my B is 1, 4, 5. So you be like, I want to make these ones zeros. That's a 0, 0, and also there. So if you want to make that a 0, someone can be like row 2. The new row 2 is going to be row 2 minus row 1. And the new row 3 is going to be row 3. Yeah, these ones I will just add plus that. Something like that. So we shall get a new A. If I try to add, so I can be like, so therefore NU. Can I call this NU? It's going to be row 2, row 1 remains the same, 1, 2, 3. Row this becomes a 0, however you're adding, so this is a 4, this is a 2, row 3 plus row 3 plus row 1, row 3 plus row 1, so this is a 0, this is a 3, this is a 4, that is a 4 also. So that is my NU, however I also have BNU. BNU I still add row 2 minus row 1, this minus that, this one remains the same, however I have 4 minus that, that's a 3, then 5 plus that, that's a 6, something like that. So I have to move with it. So so what do I do? I want to change this to my clone form. So if you find that I can further swap this, because I also don't need this. So I can create something, some row, let's say row 3 now, to be given by this can be like row 3 minus 3 out of 2, 1. Then you swap and eliminate that and form your triangular matrix. So after forming your triangular matrix, you will observe, after forming your triangular matrix, however, the triangular matrix you form, this will affect that and it will also affect that. So after forming your triangular matrix, then you will go back to using the algorithm that we used earlier. So we know that for the upper triangular matrix, the algorithm that we use, xj equals to that. Any solution, this is given by, I use the bj minus, I use the bj minus the summation from I equals to 1 up to g plus 1. This was u, j, yeah, the root remained the same. That j remains the same, is the I that keeps on changing, 10 times xi. And this is 1 out of ujj, something like that. So after completing this into the row, after removing this, then you can use our algorithm to solve for the x values. However, this not only affects this, it also affects this side. So you have to do it that way. Something like that. So whenever you have this, you will try to convert it into the upper triangular, or lower triangular using the row echelon form, then solve using the respective algorithm. So the interesting part is here. So whenever we are given our matrix and we want to change it to whenever we are given our matrix, for our linear system, Ax equals to B, and we want to use the Gaussian elimination method, this is what we are going to be doing. So we just come and be like, now there is without using what I've just done, without using the row echelon, like without using like the subtraction of the rows, columns, echelon forms, we can convert A to an upper or lower triangular matrix, and then solve. For x. So what do we do? So the first thing we do is we get from our A, we introduce a matrix. Let me call it capital M. So this matrix capital M is given by the first thing that you do. This is the first step. You get an I plus E plus small m. Can I call this m naught equals to m1, and this is also equal to m1 that, something like that. So this is instead of doing the row echelon form, like the first step, the second step, we use this. So if our A is, let's say, A11, A12, A13, continuing, A21, A22, A23, continuing, A2, A31, A32, A34, continuing like that, even down here. So what do? I get an aim. So my aim is targeting at removing these ones. You remember I want to transform it into triangular matrix, let's say upper. So I want to remove those ones and the ones which are below that. So I use m naught. So I use m naught. So this is equal to, so you find that this is going to be equal to, where I, we all know I, it is the corresponding identity matrix. The corresponding identity matrix basing on the size of A. What is M1? Can generalize them and be like, now the MJ is just this vector 0. Okay, let me say 1. M1 means that now this will be 0. It's like we are in this position. You put a 0 here, then the rest, these ones, the only way you can eliminate them, you take the minus. So this is like minus, you take A21 divide by A11. Then the second one will be negative A31 divide by A11. You take this, you divide it on these two, the lower one that you want to eliminate, then you subtract. And that will continue downwards. Then my E1 transpose, now this one is in this form. We know that E1, since it is in the 1, so meaning the 1 is there, then the rest are zeros onwards, like that. And I is that. So you see that this M naught, the first M naught you're going to create is going to be of the form, this will be 1. Yeah, it's like you're adding the identity. This is 0, this is 1 onwards. The ones will continue up to there, these will be zeros. These will be zeros. Like that. So this is plus this, so you get this, copy, so I have that. Then I also bring this, do I want this, so you bring that there. So when I go through that, this is what you get. You get 1, 0, 0. So these are the only ones which change. I don't know, I think I wrote this poorly, basing on what I had written earlier. This is the identity matrix, and we don't really know up to where, because 1 is somewhere here. These ones come to it in that way. My M naught is going, the first one will be in this form. So this is 1, 0, 0. This is negative 8 to 1. These are the only ones which change. The rest of them remain the same. A11 downwards, in case there are other cases, these ones will remain zeros. This will remain a 1. This will be 1. These ones remain zeros. Something like that. So after getting that M, now when you bring this M 0, you multiply it with the A that you had, you get what we call A1. Now this A1 is a modification of matrix A. A1 is a modification of matrix A. However, this time round, it won't have these ones. These ones will now be zeros. So my A1, after multiplying, you remember you want to take it to the upper triangular. You want to take it to the upper triangular thingy format. So now it will be this. You will get another matrix where this is A11. Now these ones will be zeros. Everything in this column downwards will be zeros. But these ones will change, of course. So they won't remain the same. Yeah, that's why I'm putting the bar, A1 bar. Now you want to also eliminate these. Yes, you have formed a new one, but you also don't need those ones. So how do you remove those ones? So you remove those ones by still multiplying. So after you getting the A1, now you continue and get the M1. Then continue to eliminate the entries A bar 2 onwards. A bar 2, A bar 3 2 downwards. Entries in that column, because you also need them to be zeros. So to eliminate those ones here, the first step was to eliminate here. The first step, this actually, let me say this helps to eliminate entries. It helps to eliminate entries. Entries of capital A, and that is entries A21, A31 onwards. Now this one helps to eliminate it. Now I create another M1, continue to eliminate that. So to eliminate those ones, I need M1 now. M1 is still given by I plus Mg. Now in this case it will be M2 because you have moved to the second column. Now this is E2 transpose that. But what is M1? This is I. What is this column vector M2? The column vector M2. Oh, by the way, I'm lying. I don't want to eliminate this. Meaning this is supposed to be from A3 to A3. This should be A4 too. Yeah, like that in that column. So meaning you keep this the first one will be 0, even the second one is 0. Now from here, this will be negative. You put a negative, then you add A2 now. You divide by this one, the upper one. You divide by the upper one. A2 now. So now this is also minus F42 divided by A2. You continue in that format downwards. So that is our I. What is this? So now here it's 1, so that is 0 onwards. Something like that. So if I get my A2 therefore is going to be gotten by multiplying now my M1 times A1. So meaning now this matrix will be in the form A1 can still be there, this one. However, it's double prime. Can bring this here. Copy. Can bring that. So this is what we have. So this is what I have. F32. Now these will be double bars. Now in this case, have eliminated this one. These ones are no longer there, based on what we have just done. Now I believe you are observing that we are continuing to simplify it, to change it into a triangular matrix. So basing on the size of the matrix, basing on A, if A is an Rn by n, then we shall achieve our upper triangular matrix will be given to us. Our upper triangular matrix will be up to when you reach the point A, n minus 1. And if you're keen, this a n minus 1 is attained by, you get the A, then you multiply m naught. If it refuses, you multiply m1. So you continue. If it refuses, you multiply m2. You follow what we have been doing, and this will go up to n minus 2. So if that is it, so this will go up to that. So that's when you attain your upper triangular matrix. This is m1, this is m0, and I've shown you how to get m1 and m0. m1, m0, something like that. Up to that. So if your matrix is a 3 by 3, if A is, let's say, a 3 by 3 matrix, then I expect to get the upper triangular when A is 2, and must be attained after multiplying. You get our A, then you multiply m naught. Then after multiplying m naught, I expect to stop on m1, like that. Then the other interesting part is that therefore, what do you see? You see that this was just an example. Hence, we see that since when I multiply n minus 2, let's say this is also n minus 3, m2, this is m1, this is m0, this is A, and this is equal to U. I don't know if people can see, if you can see that m0, this is A1. When you combine with that, that is A2. When you combine with that, that is A3. So you continue in that way. And also when I generalize all these ones, all these ones, when I get this, can call them capital M. When you multiply them, so you see that my M is equal to n minus 2, and this goes up to m naught. Therefore someone can write that my M, instead of writing them on all of them, you write MA equals to U. Okay, so therefore then someone can be like, therefore if I multiply P, if my MA equals to U, then Okay. Okay, so we see that therefore my A equals to M inverse U. So from my AX equals to U, my AX equals to B. Very sorry. For my AX equals to U, someone can instead write M inverse. Someone can instead write M inverse U M inverse U equals to B. Something like that. Something like that. Because our A is that M inverse U equals to B, but here is the X. And forgotten it, so this is M inverse U equals to B. But this M inverse members is the same as L. M inverse is the same as the lower triangular. But we know that our M is from Mn minus 2 up to M0, meaning that the inverse of this is the same as Mn minus 2 up to M0. Okay, let me say M2, M1, M0, but this entire thing is the inverse. So the inverse, we expect this to be M0 inverse. So I expect this to be M0 inverse. This is M1 inverse. You can write these ones down. It's okay. Initially I've written them up. You can go down such that the inverse is clear. M0 inverse. This is M1 inverse up to Mn minus 2. I'm writing it down. Inverse, something like that. And when you do that, you get L. So meaning that my M inverse Ux equals to B is going to be L Ux equals to B. So after getting your U, so you see now we are solving our our system Ax equals to B, whereby we have expressed A in terms of LU. In terms of LU, so we have that my LU X equals to B. My LUX equals to B, so you let my UX to be Y. So you first solve for Y using LY equals to B. Then after solving that, then you come back and solve for UX equals to Y. Something like that. Yeah. In most cases, that is what we call so we can solve our problem using that. So next time we shall do an example on how to solve this using that. Okay, have a good night. Comments should be in the comment section. So today we have basically talked about the Gaussian elimination method. Gaussian elimination method, where we try to use the normal method that we know of solving this, turning into the triangular form using the row echelon form. However, in this case we are not interested in that. We are interested in decomposing A into the lower triangular and the upper triangular using these m's, and I've tried to define how m is given, and I've also tried to define to show you how the u is defined. The u is given by this, so you should keep that in mind. And the L is the inverse of m. So after getting those, then you can form these two systems. Then you solve this one first, then you solve this one second. Next time we shall do an example. Thank you. Have a blessed day. Buon giornata. Have a blessed everything. Thank you.